Here's something that should keep you awake at night. An interstellar object just performed the same maneuver twice. Not approximately. Not kind of similar. Identical solar alignment, 8 degrees of precision, separated by millions of kilometers and months of travel. The mathematical probability of this happening randomly is 1 in 40,000. It's like watching a leaf fall from a tree, land perfectly upright, then do it again when you toss it back up. 3i Atlas shouldn't remember where the sun is. Comets tumble, they wobble, they forget. But this one hasn't. Avi Loeb has named it the 14th anomaly, and it's forcing us to ask a question nobody wants to answer out loud. So either we're witnessing the lottery winner of cosmic probability, or we're looking at controlled flight. By the end, you'll understand why both answers are equally disturbing, and why December 19th matters more than anyone's admitting. Stay with me as we cut through the noise and find the truth buried in the data. Hit subscribe because new observations about 3i Atlas are arriving hourly, and what we learn in the next few days could rewrite everything. The universe doesn't announce its revelations with fanfare. Sometimes the most important discoveries whisper, and you need to be listening when they do. Something impossible is happening right now, roughly 1.8 astronomical units from Earth. An object from another star system is performing a maneuver that should not exist in nature. The odds against what we're seeing are approximately 1 in 40,000. And yet, here it is, doing exactly what the universe says it shouldn't do. Let me be clear about what we're discussing. This isn't speculation. This isn't internet conspiracy theory. This is observational data that has professional astronomers quietly uncomfortable in faculty lounges across the world. The object is called 3i Atlas, the third confirmed interstellar visitor to our solar system, and according to Avi Loeb's latest analysis, it has just revealed what he's calling its 14th anomaly. 14 separate features that make this thing behave differently than any comet we've ever studied. But this newest one, this geometric impossibility, is the one that's keeping people awake at night. Here's what's happening. When 3i Atlas approached the sun earlier this year, its rotation axis, the invisible pole around which the entire object spins, was aligned with the sun to within approximately 8 degrees. 8 degrees might sound like wiggle room until you understand what we're measuring here. We're talking about a 3-dimensional orientation in the vastness of space. Imagine a spinning top in a completely dark room, and somehow, impossibly, the axis of that top is pointing almost exactly at a specific light bulb on the far wall. That's strange enough, but here's where it gets genuinely unsettling. As the object rounded the sun and began its departure, heading back, out toward interstellar space, it maintained that same 8-degree alignment, same orientation, same impossible precision, on approach and on departure. The mathematics here are straightforward and brutal. If you have a randomly oriented rotating object, the probability of it aligning with any specific direction to within 8 degrees is roughly 1 in 200. Do that twice, independently, and you're multiplying probabilities. 1 in 200 times 1 in 200 gives you approximately 1 in 40,000. Those are lottery ticket odds. Those are get struck by lightning odds. And yet, an icy chunk of material from beyond our solar system apparently just won that lottery without buying a ticket. Avi Loeb, the chairman of Harvard's astronomy department, and a figure who generates either admiration or exasperation, depending on who you ask, has been cataloging anomalies associated with 3i Atlas since it was first detected. Non-gravitational accelerations that suggest outgassing or something pushing the object. Spectroscopic signatures that don't quite match known cometary composition. A trajectory that brought it suspiciously close to our inner solar system, despite the astronomical improbability of such a path. Each anomaly by itself could be explained away, rationalized, fitted into our existing understanding of cometary physics with enough creative modeling. But 14 of them, stacking up like evidence at a crime scene, starts to feel less like coincidence and more like a pattern-demanding explanation. This 14th anomaly is different because it's about persistent behavior. It's not about what the object is made of, or how bright it appears, or whether it's outgassing at expected rates. It's about orientation, about the object's relationship to the sun across time and distance. If 3I Atlas were simply a chunk of ice and rock tumbling through space, heated unevenly by solar radiation, buffeted by jets of sublimating volatiles, there is no physical mechanism that should cause it to maintain a sun-facing alignment through both legs of its solar encounter. Comets tumble. They wobble. Their rotation axes precess like dying tops, tracing complex curves across the celestial sphere as different surfaces heat and cool, as jets fire asymmetrically, as the entire object responds to the chaos of solar interaction. But 3I Atlas isn't doing that. Its rotation axis, at least according to the geometry Loeb has reconstructed from observational data, has remained stable, locked, pointing at the sun like a compass needle that never wavers. And here's the detail that transforms this from astronomical curiosity to genuine puzzle. There's a jet, an anti-tail as it's called, that appears to be aligned with this rotation axis. An anti-tail is exactly what it sounds like. A tail that points toward the sun rather than away from it. A feature so rare and so counterintuitive that most people assume you're describing a mistake when you mention it, yet multiple observations confirm it. This thing has a narrow, collimated jet pointing sunward, apparently tied to its rotation axis, and that axis has maintained solar alignment across millions upon millions of kilometers of travel. Let me paint this more clearly. Imagine you're watching someone across a crowded stadium. They're spinning in place, and they're holding a flashlight that's aligned with their body's spin axis. Now imagine that no matter which way they turn, no matter how they move through the crowd, that flashlight beam always points directly at you. Always. Through their entire journey across the stadium floor. You would start to suspect that they're tracking you deliberately, that there's intention behind the pointing. Because random motion, random orientation, shouldn't produce persistent alignment. The universe is too big, angles too numerous, chaos too fundamental to allow for such precision without a mechanism to maintain it. So we're left with two possibilities, and neither of them is comfortable. Either we're witnessing a genuinely miraculous statistical fluke, the kind of coincidence that happens once per 40,000 similar objects, and we just happen to be the astronomers lucky enough to catch it. Or we're witnessing something that isn't random at all, something that has maintained its orientation deliberately. Something that is, to use the word nobody wants to say out loud in professional settings, controlled. And here's the truly wild part. As you're listening to this, as I'm recording these words in mid-December 2025, 3I Atlas is making its closest approach to Earth. Not dangerously close, we're talking about 1.8 astronomical units, roughly the distance from Earth to Mars at certain points in their orbits, but close enough that every major observatory on the planet is pointed at it. Close enough that we're getting the best data we'll ever have on this object. Close enough that if something genuinely strange is happening, if this really is the exhaust plume of a spacecraft rather than the chaotic outgassing of a comet, we're about to find out. The timing is almost theatrical. We've spent months analyzing this thing's approach geometry, debating its anomalies, watching it close in on the sun, and then begin its outbound journey. And now, at the moment of closest Earth approach, at the moment when our instruments can see it most clearly, we're forced to confront the question we've been dancing around since its discovery. What exactly are we looking at? Because the answer might be about to change everything. Or it might be nothing at all. And the only thing worse than finding out we're not alone in the universe might be finding out that we are. That we're surrounded by an empty cosmos, playing tricks with probabilities, teasing us with patterns that mean nothing, promising mysteries that dissolve into mundane explanations the moment we look close enough. December 19th, 2025. Mark that date. That's when 3i Atlas makes its closest pass by Earth, and every astronomer with access to observing time is scrambling to point their instruments at this thing. We're not talking about amateur enthusiasts with backyard telescopes, though some of them are watching too. We're talking about Hubble, the James Webb Space Telescope, the Very Large Telescope Array in Chile. Ground-based observatories across 6 continents coordinating their observations, trying to squeeze every photon of data from this object before it recedes back into the interstellar dark. And what they're seeing is genuinely bizarre, a mix of the familiar and the impossible that has the astronomical community tied in argumentative knots. Let's start with what looks normal, because there's actually quite a bit of it. 3i Atlas has a coma, that fuzzy envelope of gas and dust that surrounds active comets when they heat up near the sun. The coma is behaving more or less as expected, expanding as the object warmed during perihelion, its closest solar approach, and now beginning to dissipate as the comet moves outward. Spectroscopic analysis shows emission lines consistent with diatomic carbon, the molecule responsible for the green color that comets sometimes display when they're actively outgassing. Images from various observatories show exactly this, a greenish tint to the coma that's textbook cometary behavior. If you showed these images to an undergraduate astronomy student without context, they'd identify it as a comet without hesitation. Nothing exotic, nothing alarming, just another icy visitor getting its solar tan. The trajectory is exactly what was predicted for an interstellar object. It's following a hyperbolic orbit, which means it's not bound to our solar system. It came from somewhere else, it's not staying, and its path curves through our cosmic neighborhood with the geometry of a one-time visitor. No weird course corrections that violate orbital mechanics. No impossible accelerations that suggest hidden propulsion. The gravitational dance between 3i Atlas and our Sun is playing out according to Newton's laws, with Einstein's relativistic corrections, precisely as it should. Mission controllers for various space agencies have calculated its trajectory forward and backward, reconstructing where it came from and where it's going, and everything checks out. The math works. The physics is clean, and yet, the anti-tail is still there. That's the first genuinely weird observation that won't go away no matter how much conventional modeling you throw at it. Anti-tails are rare under any circumstances. They're typically explained as projection effects, tricks of perspective where dust grains left behind in a comet's orbital path catch sunlight at just the right angle to create the illusion of a sunward pointing tail. Except 3i Atlas's anti-tail isn't behaving like a projection effect. It's persisting. It's maintaining structure. Recent observations, just days old as I'm speaking, show this feature extending roughly 500,000 kilometers toward the sun. That's farther than the distance from Earth to the moon. We're talking about a narrow, collimated jet of material pointing at our star across a gulf wider than our own planet's satellite orbit. And it's not fading. It's not dispersing the way projection effects should. It's just there, pointing sunward like an accusing finger, defying easy explanation. The persistence is what bothers people. Comets outgas chaotically. They develop jets as subsurface ices vaporize and burst through weak points in the crust, and those jets point in whatever direction the local topography dictates. Sometimes you get jets pointing sunward, sure, but they're transient. They flicker on and off as the rotation brings different surface features in and out of sunlight. They don't maintain a single orientation across weeks of observation. They don't stay aligned with anything beyond the accident, of which crater or vent happens to be facing the sun at any given moment. Yet 3i Atlas seems to have managed exactly this trick, maintaining what appears to be a persistent sunward jet that's somehow tied to its rotation axis. Here's where the observations get genuinely puzzling. multiple independent analyses of the light curve, the pattern of brightness variations as the object rotates, suggest a rotation period of roughly several hours. That's normal for a cometary body. But the wobble, the precession you'd expect from asymmetric outgassing, from jets firing off center and imparting torque to the object, seems to be minimal. The rotation axis appears stable. Think about what that means physically. Every time a jet fires, it's essentially a tiny rocket engine pushing on the object. If that jet isn't perfectly aligned with the rotation axis, it's going to cause the object to tumble, to change its orientation over time. It's basic physics, conservation of angular momentum applied to an asymmetric body with asymmetric forces. Yet 3I Atlas's rotation axis has apparently maintained its solar alignment through all of this, through perihelion when heating would be most intense, through the activation of whatever outgassing mechanisms are producing that anti-tail, through everything that should have caused it to wobble and tumble like every other comet we've studied. Now, before we drift too far into speculation, let's acknowledge the recent research that argues for normalcy. A paper published just last month analyzed 3I Atlas's behavior in detail, comparing its observed properties against models of cometary outgassing and dynamics. Their conclusion, stated with appropriate scientific caution, is that everything observed so far falls within the boundaries of expected cometary behavior. Yes, the anti-tail is unusual. Yes, the rotation seems stable. But unusual is not impossible. The researchers point out that we've only studied a few dozen comets in sufficient detail to characterize their rotational dynamics, and that sample size is nowhere near large enough to declare that 3I Atlas's behavior is unprecedented. Statistical anomalies happen. Objects at the tail end of probability distributions exist by definition. Just because we haven't seen something exactly like this before doesn't mean it can't be a natural comet. The counter-argument, the one that keeps the debate alive, is that we're not talking about one anomaly. We're talking about 14 of them, each independently unlikely, all appearing in the same object. The color evolution, normal. The spectroscopy, mostly normal. The trajectory, perfectly normal. But the anti-tail persistence, unusual. The rotational stability, unusual. The geometric alignment with the sun, statistically unlikely. The trajectory bringing it so close to the inner solar system, improbable. Stack enough improbabilities together, and you start to wonder whether you're looking at a statistical outlier or whether your assumptions about what's possible are wrong. And there's another detail worth mentioning, one that doesn't fit neatly into either the normal or anomalous categories. The surface reflectivity, the albedo, seems to be lower than typical for cometary nuclei. Not dramatically lower, not in a way that screams artificial materials, but lower enough that it's been noted in multiple observation reports. A darker surface could mean differences in composition, perhaps more carbonaceous material than water ice. Or it could mean an older, more processed surface that's been irradiated by cosmic rays during a longer journey through interstellar space than typical Oort cloud comets experience. Or, and this is where we start edging into speculation, it could mean something about the material properties that we're not equipped to interpret because we've never encountered them before. What's clear is that every telescope looking at this thing is recording data, and that data is simultaneously confirmatory and confusing. Yes, it looks like a comet. Yes, it's behaving mostly like a comet. But there are enough edge cases, enough unusual features, enough statistical eyebrow raisers that nobody's quite ready to close the book and file this underexplained phenomena. The James Webb Space Telescope's infrared observations should tell us more about composition. Ground-based radar, if it can get a good bounce, might tell us about surface structure. Every observation is either going to strengthen the natural comet hypothesis or deepen the mystery. And the timing, again, feels almost scripted. We're getting our best data right now, in these days surrounding closest approach, and the astronomical community is basically holding its breath, waiting to see whether the observations resolve into clarity or fracture into more questions. What would convince skeptics that something genuinely strange is happening? That's the question that doesn't have an easy answer. More anomalies? We've already got 14. Stranger behavior? Hard to imagine what would be stranger than the alignment statistics we're already seeing. Direct evidence of artificial composition? That would do it, but spectroscopy hasn't shown anything obviously technological. A course correction using visible propulsion? That would end the debate instantly, but so far the trajectory remains purely ballistic. We're stuck in this uncomfortable middle ground, where the evidence is weird enough to demand attention, but not weird enough to force a paradigm shift. And so the telescopes keep watching, the data keeps accumulating, and astronomers keep arguing about probability and precedent, about whether we're witnessing a miracle of nature or something that nature didn't create at all. Avi Loeb is either the bravest astronomer of his generation or the most reckless, depending on which colleague you ask after the faculty meeting ends and the real opinions come out. He's the former chair of Harvard's astronomy department, a position of considerable prestige that typically demands a certain decorum, a certain adherence to conservative scientific interpretation. Loeb has abandoned that decorum entirely. He's built a career lately on saying out loud what other scientists might whisper in hallway conversations after a few drinks at conferences. And regarding 3I Atlas, he's saying this: the geometric alignment we're observing is not just statistically unlikely. It's a signature that demands we consider non-natural explanations. In plain English, he's suggesting we might be looking at a spacecraft. Let's be clear about what Loeb is and isn't claiming. He's not saying he has proof. He's not announcing that aliens have arrived, and we've documented their exhaust plume. What he's doing, in paper after paper and interview after interview, is arguing that the hypothesis of technological origin deserves serious scientific consideration, that it should be on the table alongside natural explanations, evaluated based on how well it fits the data, rather than dismissed because it makes people uncomfortable. And he's pointing out, with increasing frustration, that much of the astronomical community seems more interested in explaining away anomalies than in taking them seriously. The 14th anomaly, this geometric alignment that we discussed earlier, is Loeb's latest piece of evidence. He's calculated those 1 in 40,000 odds based on straightforward geometric probability. If you have a randomly oriented spinning object and you want it to align with a specific direction, to within 8 degrees, you're selecting a small solid angle out of the full sphere of possible orientations. Do that twice, on approach and departure, and you multiply the probabilities. The math isn't controversial. What's controversial is what you do with that number. Loeb argues that such low probability demands consideration of alternative hypotheses. His critics argue that low probability events happen all the time, that this is exactly the kind of selection bias you expect when you're studying unusual objects that caught your attention precisely because they're unusual. But Loeb isn't hanging his argument on this single anomaly. He's been building a case since 3I Atlas was first detected, cataloging features that don't quite fit. There's the trajectory, for instance. Previous analysis showed that the odds of an interstellar object arriving on a trajectory nearly aligned with the solar system's ecliptic plane, the plane in which planets orbit, was roughly 0.2%. Not impossible, but unlikely enough to notice. Then there are the non-gravitational accelerations, tiny changes in velocity that suggest something is pushing on the object beyond pure gravity. These are typically explained by outgassing, by jets of sublimating ice acting like tiny rocket engines. But the magnitude and timing of these accelerations, according to Loeb's analysis, don't perfectly match simple outgassing models. They're close, but not quite. And then there's the question of what we're not seeing. If 3I Atlas is a natural comet, we'd expect certain features. We'd expect a dusty coma. Check, it has that. We'd expect volatile ices. Check. Spectroscopy suggests water and carbon compounds. But we'd also expect irregular shape, the potato-like morphology that characterizes most small solar system bodies that have never been large enough to crush themselves into spheres under their own gravity. We don't have resolved images of 3I Atlas's nucleus. It's too small and too far away for that level of detail. But the light curve, the pattern of brightness changes, suggests a relatively regular shape, not dramatically irregular. Not the wild brightness variations you'd expect from a highly elongated tumbling object. Again, not impossible for a comet, but not typical either. Loeb has also waded into controversy by publicly criticizing what he perceives as institutional bias against considering non-natural explanations. He's argued in various interviews and articles that NASA and other space agencies have a vested interest in maintaining that life beyond Earth, if it exists, is either microbial or located so far away that we'll never encounter evidence of it. Accepting that we might be observing technological artifacts would force uncomfortable questions about whether we've missed previous visitors, whether our search methodologies are adequate, whether the universe is more populated than our models suggest. He's accused parts of the scientific establishment of motivated reasoning, of being more interested in protecting consensus than in following data wherever it leads. The pushback from the mainstream astronomical community has been swift, and in some cases, fairly brutal. Critics point out that extraordinary claims require extraordinary evidence, and that statistical improbability is not evidence of anything except statistical improbability. They argue that Loeb is engaging in what amounts to motivated reasoning himself, that he's starting with a desired conclusion, alien technology, and then selecting and interpreting data to support that conclusion, while downplaying evidence that supports more mundane explanations. Multiple papers have been published specifically addressing 3I Atlas's properties, and arguing that every observed feature can be explained by conventional cometary physics without invoking anything exotic. The statistical argument gets particularly heated. Critics point out that when you study an object that caught your attention because it was unusual, you're already looking at something from the tail of a probability distribution. Calculating odds after the fact and acting surprised that they're low is a classic error in statistical reasoning. It's like shuffling a deck of cards, dealing out a specific hand, and then calculating the odds of getting exactly that hand. Yes, it's 1 in 52 factorial, an astronomically small probability. But some hand had to appear, and whatever hand appeared would have been equally unlikely. The question isn't whether 3I Atlas's properties are unlikely. It's whether they're more unlikely under natural explanations than under technological explanations. And that's a much harder calculation to make, requiring assumptions about alien technology that we have no basis for making. There's also the question of consistency. Oumuamua, the first confirmed interstellar object detected in 2017, also had anomalies. It also had non-gravitational accelerations that didn't perfectly fit outgassing models. It also had unusual properties that Loeb argued suggested possible technological origin. The astronomical community largely rejected that interpretation then, and many of the same scientists are rejecting it now for 3I Atlas. The patterns, critics say, is that Loeb sees artificial objects everywhere, that his threshold for proposing alien technology is far lower than scientific standards should allow. If every unusual object is potentially a spacecraft, then the hypothesis loses its explanatory power. It becomes unfalsifiable, a just-so story that can be retrofit to any observation that doesn't immediately conform to our first-pass models. And yet, and this is where the debate gets genuinely interesting, Loeb's critics can't quite dismiss him entirely. He's not a crackpot. His credentials are impeccable. His mathematical analysis, even when controversial in interpretation, is technically sound. He's published hundreds of papers in legitimate journals on topics ranging from black hole physics to cosmology. When he makes an argument, even one that most of his colleagues disagree with, He makes it in the language of physics and statistics, backing it with calculations that can be checked and reproduced. You can argue that he's wrong, that he's overinterpreting data, or making unwarranted assumptions. But you can't argue that he's ignorant of the science, or that he's arguing in bad faith. So we're left with this uncomfortable standoff. On one side, a prominent astronomer arguing that we should seriously consider the possibility that an interstellar object is exhibiting behavior inconsistent with natural processes. On the other side, the majority of the astronomical community arguing that every observation to date fits within the boundaries of known comet physics, unusual perhaps, but not impossible. Both sides are looking at the same data. Both sides are applying legitimate statistical and physical reasoning. They're arriving at radically different conclusions about what we should infer from those 1 in 40,000 odds, from that persistent anti-tail, from the whole constellation of anomalies that characterize this object. And the resolution, if it comes at all, will come from more data, from better observations during this closest approach period, from future interstellar visitors that either repeat the pattern or prove 3I Atlas was a one-off oddity. The debate continues because the evidence, frustratingly, points in both directions at once. We need to talk about what an anti-tail actually is, because the name is almost perfectly designed to confuse people. When you picture a comet, you're imagining that classic image, a bright head with a long, luminous tail streaming behind it, away from the sun, pointing back along the comet's orbital path like cosmic hair blown by solar wind. That's the normal configuration. Solar radiation and the solar wind, that stream of charged particles constantly flowing outward from our star, push the gas and dust away from the comet, creating a tail that always points away from the sun regardless of which direction the comet is actually traveling. It's one of the most reliable features in cometary astronomy, so reliable that you can determine the direction to the sun just by looking at which way a comet's tail points. An anti-tail breaks this rule. An anti-tail appears to point toward the sun, and when you first see one in an image, your immediate reaction is to assume there's been a mistake, that the image has been reversed or mislabeled, because what you're seeing shouldn't be physically possible. Except it is possible, under very specific and usually temporary circumstances. The standard explanation involves orbital geometry and projection effects. Imagine the comet is leaving behind a trail of dust particles in its orbital path, a debris stream of material that's been shed over days or weeks. These particles are no longer moving with the comet. They're in their own slightly different orbits, lagging behind. Now imagine you're viewing this system at just the right angle, from just the right position, such that this debris trail appears to extend forward from the comet toward the sun, even though in three-dimensional space, it's actually extending back along the orbit. It's a perspective trick, a projection effect, no more mysterious than the way train tracks appear to converge at the horizon, even though they're parallel. That's the textbook explanation, and it works beautifully for most observed anti-tails. They appear briefly, they fade as viewing geometry changes, and they behave exactly as you'd expect from sunlit dust particles arranged in a curved orbital path. But 3I Atlas's anti-tail isn't behaving like a projection effect. It's persisting. Multiple observations, taken from different angles as Earth moves in its orbit, continue to show this sunward pointing feature. It's not fading. It's not changing geometry in the way a projection effect should. And perhaps most troubling, it's maintaining extraordinary collimation. It's narrow, focused. Recent measurements put its length at approximately 500,000 kilometers, which is genuinely staggering when you try to visualize it. That's roughly 1.3 times the Earth-Moon distance. It's a jet of material pointing at the sun across a span that could fit our planet and its satellite with room left over. The physics of maintaining such a structure is not trivial. If this is outgassing, if this is sublimating ice turning to vapor and carrying dust particles outward from the nucleus, then something is collimating that flow. Something is keeping it narrow rather than letting it expand into a broad coma the way most cometary jets do. On Earth, we collimate gas flows using nozzles, carefully shaped openings that constrain the expansion and direct the flow in a specific direction. In nature, you can sometimes get collimation from magnetic fields or from the geometry of a deep fissure or vent that constrains the flow's initial direction. But maintaining that collimation across 500,000 kilometers is asking a lot of natural processes. Gas expands, particles scatter. The further you get from the source, the more the flow should spread out, following basic physics of pressure and density gradients. Yet here it is, this impossibly narrow jet, apparently aligned with the object's rotation axis, apparently maintaining its structure across distances that dwarf anything we've seen in solar system comets. And here's where the geometry becomes genuinely confounding. If the jet is tied to the rotation axis, and if that rotation axis has maintained solar alignment as Loeb claims, then we're looking at a feedback loop that shouldn't exist in nature. The jet is pointing sunward because the rotation axis is pointing sunward. But why is the rotation axis pointing sunward? Asymmetric outgassing from jets typically causes comets to tumble, to wobble, to change their orientation over time. The torques from jets should cause precession. Yet, we're not seeing significant precession. We're seeing stability. Think about a spinning figure skater. When they pull their arms in, they spin faster due to conservation of angular momentum. When they extend one arm, they start to wobble, to precess, because they've created an asymmetry in their mass distribution. Now imagine that figure skater is also carrying a fire extinguisher and occasionally shoots a blast of CO2 from it. That jet of gas is going to push them, going to change their motion, going to introduce torques that cause them to wobble even more. That's what should happen to a comet with active jets. The jets introduce asymmetric forces that couple to the object's rotation, causing complex tumbling and precession. Yet 3I Atlas seems to have avoided this, maintaining a stable rotation axis despite presumably having active outgassing that's producing that anti-tail. One possible explanation involves the source of the outgassing being located at one of the rotational poles. If the jet originates right at the pole, then it's aligned with the rotation axis by definition, and the torques it produces are minimized because the lever arm is essentially zero. You're pushing along the rotation axis rather than off to the side, so you're not introducing the asymmetric forces that cause wobbling. This can happen naturally if volatile ices are more concentrated at polar regions, if the thermal processing of the object's surface has left more ices exposed at locations that receive less average sunlight over a rotation cycle. It's not common, but it's not impossible either. But here's the problem with that explanation. It doesn't account for the solar alignment. Even if the jet originates at a pole, even if the rotation axis is stable as a result, there's no reason that poles should point at the sun. The orientation of the rotation axis relative to external directions, like the sun, should still be random unless there's a physical mechanism maintaining that alignment. And what mechanism could do that? Solar radiation pressure is too weak. Magnetic interactions with the solar wind are negligible for a presumably non-magnetized comet. Gravitational gradients, tidal forces, those scale with distance cubed and are essentially zero at the distances we're talking about. There's no known natural force that should cause a comet's rotation axis to lock onto the sun and maintain that orientation across millions of kilometers of travel, unless the alignment isn't being maintained by external forces, unless it's being maintained by the jet itself. Here's where we enter genuinely speculative territory. Imagine the jet is functioning like a thruster, like a control system that's actively adjusting the object's orientation. Every time the axis starts to drift away from solar alignment, the jet fires asymmetrically or changes its thrust vector, pushing the object back into alignment. This is how spacecraft maintain attitude control. This is how we keep satellites pointing in specific directions. But it requires active control, requires sensors to detect orientation and actuators to correct it. It requires, in short, exactly the kind of system you'd expect on a technological object, and not at all the kind of system you'd expect on a lump of ice and rock from another star system. The mental gymnastics required to maintain both positions simultaneously, that this is a natural comet and that it's exhibiting controlled orientation, creates a kind of cognitive tension that you can see in the published papers. Natural explanations require stacking unlikely circumstances, polar jets, exactly the right volatile distribution, minimal torques, stable rotation. Each individual requirement is possible, but together they add up to something that feels contrived. Technological explanations require accepting something that fundamentally changes our understanding of the universe, that we're not alone, that another civilization exists or existed, that we're observing one of their artifacts. Each position has its own burden of implausibility. Each requires you to believe something that seems unlikely. And the anti-tail just sits there in the telescopic images, 500,000 kilometers long, pointing at the sun, refusing to conform to easy explanations. The mystery remains unsolved, and every additional observation seems to deepen rather than resolve the puzzle. Let's do something uncomfortable. Let's actually lay out both cases, natural and artificial, with the same rigor we'd apply to any scientific hypothesis. Not as a debate to win, but as an exercise in honest evaluation. Because the truth is, both explanations face serious challenges, and pretending otherwise doesn't serve anyone's understanding. The natural comet hypothesis starts with a significant advantage. We know comets exist. We've studied hundreds of them. We understand the basic physics of how ice sublimates, how dust gets dragged along with expanding gas, how solar heating drives activity. When we apply this known physics to 3I Atlas, we get a lot of matches. The spectroscopy shows water vapor, carbon compounds, diatomic carbon that produces the green color. These are exactly what you'd expect from an icy body heated by solar radiation. The coma is there, fuzzy and expanding, consistent with outgassing. The brightness increases as the object approached the sun and decreases as it recedes. Textbook behavior for solar-driven activity. If you showed these observations to a comet expert without mentioning the anomalies, they'd immediately classify it as a comet without hesitation. The composition appears to be within the range of known cometary diversity. Polarimetric studies, which analyze the polarization of reflected sunlight, show characteristics consistent with cometary dust. The ratio of different volatiles, water to carbon dioxide to other species, falls within observed ranges, even if it's toward one end of those ranges. Recent studies have specifically addressed the question of whether 3I Atlas could be a natural object, and the conclusion from multiple independent groups is, yes, everything observed so far can be explained by conventional cometary physics without requiring exotic mechanisms. The non-gravitational accelerations fit outgassing models when you allow for reasonable variations in volatile distribution and activity patterns. The trajectory, while statistically unlikely, is not impossible for an object ejected from another stellar system. So, where does the natural hypothesis struggle? The anti-tail persistence is a challenge. Projection effects should change as viewing geometry changes, and we're not seeing that. The collimation, that narrow 500,000 kilometer jet, is unusual for cometary outgassing, which typically spreads into a broad coma. The rotational stability, the apparent lack of wobble despite active jets, requires specific configurations that aren't typical. And then there's the geometric alignment, that 1 in 40,000 coincidence that Loeb keeps emphasizing. Each of these can be explained individually. Polar jets can produce collimation. Specific volatile distributions can minimize torques. statistical flukes happen. But together, they require you to accept that 3I Atlas is an unusual comet, one that sits at the intersection of several low probability configurations. Not impossible, but definitely in the tail of the distribution. Now, let's consider the artificial hypothesis, and let's be specific about what that would mean. We're not talking about aliens in spacesuits with control panels. We're talking about a technological object, probably a probe of some kind, that was launched by a civilization somewhere in our galactic neighborhood at some point in the past. Could be recent, could be millions of years ago. The object passed through our solar system, possibly by design, possibly by chance. What we're seeing as the anti-tail is not outgassing, but exhaust. A propulsion plume from some kind of drive system that happens to be oriented sunward. The geometric alignment is not coincidence, but deliberate. The object is maintaining its orientation for reasons related to its mission profile or operational requirements. What observations would this hypothesis explain? The persistent solar alignment makes sense if the object is actively controlling its orientation, if it has sensors that detect the sun's direction and thrusters or other actuators that maintain pointing. The anti-tail's collimation makes sense as a focused propulsion plume rather than diffuse outgassing. The rotational stability makes sense if there's an attitude control system maintaining it. The spectroscopic signatures, the water and carbon compounds, could be propellant byproducts or ablative material from the propulsion system rather than primordial ice. Even the trajectory, arriving on a low inclination path that brought it through the inner solar system, makes sense as a deliberate route rather than a random orbit. But here's where the artificial hypothesis faces its own severe challenges. First, energy budget. If that anti-tail is propulsion, we need to account for where the energy is coming from. 500,000 kilometers of visible exhaust implies either enormous energy expenditure, which would require a power source we should be able to detect, or extremely efficient conversion of small energy inputs into visible signatures, which would require technology we can't model. Second, why is it outgassing normal cometary volatiles? If this is a spacecraft, why does spectroscopy show water vapor and diatomic carbon rather than exotic propellants or obviously artificial compounds? You could argue the propulsion system uses water or other common molecules, but that requires specific assumptions about alien engineering that we have no basis for making. Third, there's the Occam's razor problem. The artificial hypothesis requires us to accept multiple extraordinary propositions: that alien civilizations exist, that they build interstellar probes, that one of those probes happened to pass through our solar system in the brief historical window when we have telescopes to detect it, and that its design happens to mimic many features of natural comets while adding a few anomalies. Each of those propositions carries its own burden of proof. The natural hypothesis requires us to accept that we're seeing an unusual but not impossible natural object, which is a much smaller assumption. In science, when two hypotheses both fit the data, we favor the one that requires fewer unsupported assumptions. That's not a guarantee of truth, but it's a reasonable heuristic. Fourth, the pattern problem. If 3I Atlas is artificial, what about Oumuamua? It also had anomalies. It also had non-gravitational accelerations. Are we saying that 2 out of 3 detected interstellar objects are spacecraft? That would imply the galaxy is absolutely swarming with artificial objects, that they outnumber natural interstellar comets by huge margins. That's a strong claim requiring strong evidence, and the evidence we have is compatible with both being unusual natural objects. And if we say only 3I Atlas is artificial while Oumuamua was natural, we need to explain what makes this one different beyond the fact that it has more analyzed anomalies, which could just mean we're studying it more thoroughly. So let's be honest about the state of play. The natural hypothesis requires accepting some unusual coincidences, but remains within the bounds of known physics and observed cometary diversity. The artificial hypothesis explains the specific anomalies more elegantly, but requires accepting much larger assumptions about the prevalence of alien technology and the nature of interstellar travel. Neither position is obviously correct. Neither position is obviously wrong. And that, fundamentally, is why this debate generates so much heat. We're not arguing about clear-cut evidence pointing in one direction. We're arguing about how to weight different types of unlikeliness, how to balance explained data against unsupported assumptions, how much skepticism to maintain versus how much openness to paradigm-shifting possibilities. What would resolve it? Direct evidence would. If we detected radio signals from 3i Atlas, if we saw obvious course corrections that couldn't be explained by outgassing, if spectroscopy revealed synthetic compounds, or unusual isotopic ratios inconsistent with natural formation that would tilt heavily toward artificial. Conversely, if we resolved the nucleus and saw an irregular shape, if we detected rotation wobble that had been obscured by observational noise, if detailed modeling showed that the geometric alignment was an artifact of viewing angle rather than real orientation, that would tilt heavily toward natural. We're waiting for evidence that discriminates between hypotheses rather than being compatible with both. And until that evidence arrives, we're stuck in this uncomfortable space where both interpretations remain on the table, and the scientists with equally legitimate credentials can look at the same data and reach opposite conclusions. The universe isn't obligated to make its mysteries easy for us to solve, and 3i Atlas is demonstrating that principle with frustrating clarity. There's a fascinating sociological phenomenon that happens whenever astronomers announce something genuinely unusual. The scientific community analyzes the data, debates interpretations, publishes papers arguing for various explanations. And then, in parallel, sometimes intersecting but mostly separate, the internet explodes. Forums light up. YouTube channels pump out videos with increasingly dramatic titles. Reddit threads spiral into 1,000 comment debates about government cover-ups and alien motivations. Twitter, or X as it's awkwardly called now, becomes a battleground of hot takes and conspiracy theories. And watching this unfold around 3i Atlas has been, if nothing else, a masterclass in how information propagates and mutates in modern media ecosystems. Let's be clear about what we're observing in these spaces. Most of it is speculation, pure and simple. People taking the legitimate scientific questions about anomalies and extrapolating them into elaborate scenarios involving alien motherships, interstellar wars, ancient civilizations seeding the galaxy with probes. There's a whole genre of YouTube videos claiming that 3i Atlas is definitely artificial, that governments know this and are covering it up, that December 19th, 2025 will be some kind of revelation day when the truth is disclosed. None of this is based on evidence. None of this is what actual astronomers studying the object are saying, but it's spreading, and it's shaping public perception of the whole phenomenon in ways that are honestly kind of concerning. Why do people latch onto these narratives? Part of it is just the inherent appeal of mystery. An object from another star system, behaving in ways that scientists find puzzling, naturally, triggers imagination. We're pattern-seeking creatures. We're storytelling animals. When we encounter gaps in explanation, our brains want to fill those gaps with narrative, and alien intelligence is a compelling narrative. It's more exciting than saying we need better data to distinguish between unusual natural comet and extremely unusual natural comet. Part of it is also distrust of institutions and experts. There's a significant portion of the population that assumes whenever scientists say, "we don't know," what they really mean is, "we know, but we're not telling you." This assumption, largely unfounded, turns every unexplained phenomenon into potential evidence of conspiracy. But there's another element that's worth taking seriously, which is that science itself has a complicated relationship with speculation. Officially, scientifically, we're supposed to follow evidence where it leads, maintain skepticism about claims that lack support, proportion belief to available data. That's the methodology. That's what separates science from other ways of knowing. But in practice, scientists speculate all the time. We propose hypotheses that go beyond current data. We imagine scenarios that haven't been observed yet. We write papers about what we might expect to find if X were true, even if we haven't found it yet. The difference, supposedly, is that we clearly label speculation as speculation, and we subject it to rigorous testing. But to outsiders, to people following the story through press releases and popular articles, that distinction isn't always clear. When Avi Loeb says we should consider technological origin as a hypothesis worth investigating, some people hear that as Loeb claims it's definitely alien, and the message gets amplified and distorted through each subsequent retelling. The Oumuamua saga illustrated this perfectly. Loeb proposed that Oumuamua's non-gravitational acceleration could be explained by solar radiation pressure if the object were extremely flat and thin, like a light sail. He wrote a whole book about it, arguing that this hypothesis deserved consideration alongside natural explanations. The media coverage transformed this into Loeb claims Oumuamua is an alien spaceship, which he didn't quite say, but also didn't strongly push back against. The internet then transformed that into Oumuamua is definitely a spaceship, and scientists are covering it up. Now with 3i Atlas, we're watching the same pattern repeat. Legitimate scientific debate about anomalies becomes evidence of alien visitation, becomes proof of government conspiracy, becomes content for channels that thrive on sensationalism. And look, there's a version of this phenomenon that's relatively harmless. People are interested in space. They're excited by the possibility of alien life. They want to believe that we're not alone in the universe, and unusual astronomical phenomena become hooks for that hope. Fine, that's not necessarily problematic. Where it becomes problematic is when speculation disconnects entirely from evidence. When people become so invested in a particular narrative that they start rejecting contradictory information, when belief systems form around claims that haven't been substantiated. There are people right now who are absolutely convinced that 3i Atlas is an artificial object, that this is the most significant discovery in human history, that December 19th will be remembered as First Contact Day, or something equally dramatic. And when that doesn't happen, when the object passes closest approach, and astronomers announce that it's still unclear whether we're seeing unusual natural behavior or something else, those people are going to feel betrayed. They're going to assume cover-up rather than accepting that reality is more ambiguous than their preferred narrative suggested. The truly weird part is that some of the speculation comes from people with legitimate scientific backgrounds, not just Loeb, who's a tenured professor at Harvard, but other scientists who engage with these questions in public forums. There's a phenomenon in science communication where the desire to be interesting, to capture attention, to say something novel, can lead people to emphasize the most exotic interpretations over the most likely ones. When you're writing a paper, you hedge carefully, you qualify claims, you present multiple interpretations. When you're giving a public talk or doing an interview, there's pressure to simplify, to dramatize, to give people a compelling narrative. And sometimes that process transforms genuinely uncertain questions into apparent certainties, transforms speculation into claims. It's also worth noting that the history of astronomy is full of false alarms and premature conclusions. In the 1800s, astronomers reported canals on Mars and interpreted them as evidence of intelligent engineering. Turned out to be optical illusions and observer bias. In the 1960s, the discovery of pulsars led some to briefly consider whether they might be artificial beacons from alien civilizations, before realizing they were rotating neutron stars. In the 1990s, The announcement of possible microbial fossils in a Martian meteorite made huge news before subsequent analysis cast doubt on the biological interpretation. Every generation of astronomers has encountered phenomena that seem to challenge natural explanation, and every time, so far, natural explanations have eventually prevailed. Does that mean Three-Eye Atlas is definitely natural? No. History not repeating itself is always an option. Just because previous anomalies turned out to have conventional explanations doesn't guarantee this one will. But it does suggest maintaining skepticism, remembering that unusual is not the same as impossible, that our ignorance of a natural mechanism doesn't prove a non-natural one exists. The speculation spiral surrounding Three-Eye Atlas is understandable, even predictable, but it's not particularly helpful for actually figuring out what we're looking at. What's helpful is more observations, better data, careful analysis that considers all hypotheses without prejudging which one we'd prefer to be true. And that work is happening in observatories and research institutions around the world by scientists who are as curious as anyone about what this object really is, but who are committed to letting evidence rather than preference guide their conclusions. While we've been obsessing over whether an interstellar comet is exhibiting impossible geometry, the universe has been busy demonstrating that reality is routinely stranger than we have patience to imagine. The past year, 2025 specifically, has delivered a cascade of astronomical discoveries that would individually be career-defining moments for the researchers involved and collectively paint a picture of a cosmos far weirder and more active than our models comfortably accommodate. Let's zoom out, because Three-Eye Atlas isn't happening in isolation. It's part of a broader pattern of observations that challenge, complicate, and occasionally shatter our understanding of how the universe works. And some of these recent discoveries are just as mind-bending as anything involving potential alien spacecraft, if only they got the same press coverage. Start with gamma ray, burst 250 314 alpha, detected earlier this year. Gamma ray bursts are already among the most violent events in the universe, catastrophic explosions that release more energy in seconds than our sun will produce in its entire lifetime. They're typically associated with the collapse of massive stars into black holes, or the collision of neutron stars, events so energetic that we can detect them from billions of light years away. GRB 250 314 alpha is special because of its redshift, the stretching of its light due to cosmic expansion, which places it extremely early in the universe's history. We're talking about an event that occurred when the universe was less than 1 billion years old, when the first generations of stars were still forming. And here's the problem. According to our models of stellar evolution, massive stars that can produce gamma ray bursts shouldn't exist yet at that epoch. They require multiple generations of star formation, require earlier stars to have lived and died and seeded the universe with heavy elements. Yet, here's GRB 253-14 alpha blasting its signature across the early cosmos, telling us that somehow, some way, massive stars formed faster than we thought possible. The implications ripple through cosmology, forcing revisions to models of early galaxy formation and chemical enrichment. It's a reminder that the universe doesn't consult our theories before deciding what's possible. Then there's the Alaknanda galaxy, a discovery from the James Webb Space Telescope that has galaxy formation theorists frantically rewriting their simulations. JWST was designed specifically to look at the earliest epochs of cosmic history, to peer back through 13+ billion years of light travel time and see what galaxies looked like when the universe was young. What we expected to find were small, irregular, primitive structures, proto-galaxies just beginning to assemble from clouds of primordial gas. What JWST is showing us, repeatedly and disturbingly, are massive, organized, spiral galaxies that seem to have formed far too early. Alaknanda is one of the most striking examples. A grand design spiral galaxy. The kind of mature structure we associate with galaxies, billions of years old, existing when the universe itself was only a few 100 million years old. The rotational velocities, the stellar masses, the morphological features all suggest a level of organization that shouldn't be possible yet. It's like finding a modern city in archaeological layers that should only contain hunter-gatherer campsites. Something about our understanding of how galaxies form and grow must be wrong, and the JWST observations are hammering that point home with discovery after discovery. Move to exoplanet science, which has exploded into one of the most data-rich fields in astronomy over the past decade. We've gone from knowing of 0 planets outside our solar system 30 years ago to having confirmed thousands, with tens of thousands more candidates waiting for verification. And the diversity is staggering. Hot Jupiters orbiting closer to their stars than Mercury orbits our sun. Super-Earths with no analog in our solar system. Systems with multiple planets in perfect orbital resonance. Planets orbiting binary stars in configurations that seem dynamically unstable, but persist anyway. Recent atmospheric characterization has added another layer of weirdness. We've detected silicon monoxide in the atmosphere of hot Jupiters, a molecule that requires temperatures so extreme that rocks vaporize. We've found evidence of metallic clouds, raining iron and glass on tidally locked worlds, where one hemisphere perpetually faces the star, while the other freezes in eternal darkness. The chemistry happening in these atmospheres is alien in the most literal sense. Combinations of temperature, pressure, and composition that produce molecules and weather patterns Earth never experienced. Each new detection refines our understanding of planetary physics and expands the envelope of what counts as a planet. And it all points toward the same conclusion. Planetary systems are common. Diversity is the rule rather than the exception. And the universe is teeming with worlds, even if most of them are nothing like home. And then there are the organic compounds showing up in places we didn't expect. Sample return missions from asteroids, particularly Bennu via the OSIRIS-REx mission, have delivered pristine material from the early solar system directly to laboratories on Earth. What we're finding is chemically complex stuff. Amino acids, nucleobases, sugars, the building blocks of biochemistry, present in concentrations and varieties that suggest organic chemistry isn't rare or difficult in space. It's routine. It happens wherever you have carbon, hydrogen, oxygen, nitrogen, and the energy to drive reactions. The implication is profound. The raw materials for life as we know it aren't restricted to Earth. They're abundant. They're present in asteroids, in comets, in the molecular clouds where stars form. Every planetary system probably has access to the chemical ingredients necessary for biology. Whether those ingredients actually assemble into living systems is a separate question, one we still can't answer with certainty. But the preconditions, the chemistry that makes life possible, appear to be cosmically common. And that shifts the conversation about whether we're alone from a question about whether organic chemistry can happen elsewhere to a question about whether the specific sequence of events that leads from organic chemistry to biology is rare or inevitable. What does all of this have to do with 3i Atlas? Everything and nothing. Everything in the sense that each of these discoveries is part of the same larger project, trying to understand how the universe works at every scale from molecules to galaxies, trying to piece together the story of matter and energy from the Big Bang to the present. Nothing in the sense that none of these discoveries directly inform whether an interstellar comet is exhibiting controlled behavior or just unusual natural physics. But contextually, they matter. They establish that the universe is routinely surprising, that our models are frequently wrong or incomplete, that phenomena we don't immediately understand turn out to be natural processes we hadn't accounted for. That's not an argument that 3i Atlas must be natural. It's an observation that the universe has earned our humility, that unexpected doesn't mean impossible, that our ignorance of a mechanism doesn't prove a mechanism doesn't exist. And looking forward, the pace of discovery isn't slowing. The JWST is still in the early phases of its mission, still returning transformative data on a weekly basis. The Vera Rubin Observatory, with its massive camera and ability to survey the entire visible sky every few nights, is about to come online and will revolutionize time domain astronomy, catching transient events and discovering objects like 3I Atlas at unprecedented rates. The Square Kilometer Array, once completed, will be the most sensitive radio telescope ever built, capable of detecting faint signals from the early universe, or, hypothetically, from technological civilizations if they're out there transmitting. We're entering an era of astronomy where data abundance, not data scarcity, is the limiting factor, where machine learning algorithms sift through petabytes of observations looking for patterns humans would never notice, where the bottleneck shifts from collection to interpretation, from seeing things to understanding what they mean. 3I Atlas, in this context, becomes a test case. It's one object, one puzzle, one anomaly in a universe full of them. How we handle it, how we evaluate competing hypotheses, how we communicate uncertainty to the public, how we maintain scientific rigor while remaining open to paradigm-shifting discoveries. All of that will inform how we handle the next anomaly and the one after that. Because they're coming. The universe guarantees it. Every time we build a better telescope, every time we look at the sky with new eyes, we find things we didn't expect. Most of them turn out to have natural explanations. Some of them remain mysterious for years or decades before yielding to better models. And maybe, just maybe, one of them eventually proves to be evidence of something that forces us to rewrite the story we tell ourselves about our place in the cosmos. We don't know yet whether 3I Atlas is that object. But we're watching, we're measuring, we're analyzing, and we're trying very hard to distinguish between what we hope is true and what the data actually supports. That's the work. That's always been the work. And it continues. One observation at a time, one anomaly at a time, slowly building toward whatever understanding the universe permits us to achieve. The object is still up there right now, at this very moment, crossing the vast darkness between our world and where it came from. Telescopes are still tracking it. Data is still accumulating, and we're all waiting to see whether the answer, when it finally comes, will be mundane or miraculous. Because the thing about anomalies is that they only stay anomalies until we figure them out. And figuring them out, regardless of what the answer turns out to be, is why we keep looking up.